Picture a constellation of NASA's satellites, an orbiting sensor web designed to monitor the Earth like a networked sentinel, enabling us to learn vital information about one of nature's greatest threats, hurricanes. New research lets us see inside hurricanes like never before, to look under the hood and discover how the mighty engines of these storms work. Each summer and fall, the United States faces sieges from tempests whirling out of the tropics. Damage amounts to billions of dollars a year, from freshwater flooding, inundation by giant waves, and the force of 100-mile-per-hour-plus winds. Isabel was one of the most intensely monitored hurricanes ever, thanks to the current fleet of research satellites on orbit. NASA and NOAA collected thousands of images, and experts have been busy with the data. Isabel came to life in a continent half a world away, over far eastern Africa. At first, it was just a disturbance, tracked here in the clouds, beginning as a humble ripple in a steady flow of easterly tropical winds. Crossing the border between the fertile Sahel and the hot, parched Sahara, the cloud disturbance strengthened. The colors here show rain intensity, measured inside the clouds by the Tropical Rainfall Measuring Mission. Once out to sea, the warm waters of the Atlantic incubated the cloud disturbance. The cloud seedling rapidly transformed into Hurricane Isabel. As the core of Isabel warmed, the engine revved faster, and the winds whipped around the center at nearly 160 miles per hour. When it ultimately made landfall in the North Atlantic, Isabel had weakened markedly, but still remained a giant storm that devastated much of the mid-Atlantic. The ultimate energy source for hurricanes is the warmth of tropical oceans. The warm waters evaporate, and water vapor is the fuel that powers hurricane heat engines. But hurricanes feed back on the oceans that sustain them. The winds churn up the top layer of water, mixing up colder water from below. As this visualization shows, colder water trails in the wake of Hurricane Fabian. The waters have been chilled by 10 degrees Fahrenheit. But the high August sun warms the waters back up, just as Isabel crosses what's left of Fabian's wake. If we could peer under the hood of a hurricane heat engine, this is what we'd see. Satellites such as TRIM and QuickScat allow us for the first time to visualize the 3D anatomy of the storm. In a specially outfitted NASA DC-8, researchers probe the dynamics of a storm from the inside out. With periodic drops of precise instruments called dropsondes, vital data streams in that might otherwise be inaccessible, like temperature readings of the hurricane's eye. NASA's ER-2 also gathers hard-to-get data. Flying high above living, breathing hurricanes, elite pilots skirt the edge of the stratosphere to collect critical temperature and pressure data and other measurements. During a landmark mission called KMEX, these virtual satellites extended scientific vision on hurricanes immeasurably. Intense tropical rains fall from thunderclouds that ring the eye and create graceful spiral rain bands. A circular area occupies the tops of storms, warmed by giant rain clouds. Warm air, being less dense, weighs less, meaning the atmospheric pressure in the center of the storm drops. Into this low-pressure region, the air starts to swirl, turned counterclockwise by the Earth's spin, creating powerful winds that whip up enormous waves. Water vapor rising in updrafts through giant thunderclouds called hot towers condenses as the air cools. This condensation causes rain, and in the process releases latent heat into the atmosphere. Hot towers are the cylinders that do the work in the hurricane heat engine. Occasionally, during the early stages of a tropical storm, especially deep and vigorous hot towers called chimney clouds soar above all the other cloud tops. These amazing clouds are short-lived, but during their intense lives release a tremendous amount of latent heat inside the storm. If hot towers are the cylinders that power hurricane heat engines, chimney clouds are fuel-injected turbocharged versions. Rain is merely the byproduct of condensation in the atmosphere. It's what falls out of the heat engine after heat energy gets transferred upwards in clouds. The volume of rainwater produced by a hurricane during its lifetime is staggering, as much as 400 trillion tons in the case of Isabel. When this amount of water falls over land, the result can be catastrophic flooding and great loss of life. So, armed with all of this new knowledge about hurricanes, how are experts using it to save lives? These rich data sets not only enable us to better understand the physics of how hurricanes work, but provide input into sophisticated mathematical models that predict hurricane formation and behavior. NASA runs such a model on one of the world's fastest supercomputers, called Project Columbia. In this animation of the model's output, a single run captured the simultaneous formation of many hurricanes around the globe. Models like this, based on carefully collected data from NASA and NOAA satellites, deliver the most useful weather predictions. And they're improving every day. Better predictions means better hurricane protection for people around the world.
This is something I hope I never wake up until in the morning and see on the morning news, which is 5 enormous storms bearing down on the United States. Now, this is a montage of the 5 terrible storms that swept up and hit the Gulf Coast during 2005: Dennis, Emily, Katrina, Rita, and Wilma. Since 1995, we've had an amazing number of hurricanes in the Atlantic Basin. We average about 8 to 10 of these storms a year. Yet since 1995, we've been pushing 20, 25, 27 storms in certain years. 1995 began off with 21 storms. In 2004, we had an amazing number of storms. 4 hit Florida, one after another. In 2005, 27 storms. So what is going on? Kids are asking these questions. We, as educators, have got to be getting the message across to them. 2005, 17 records were set in terms of number of hurricanes, costliest storms, strongest storms, deadliest storms. So now what I'd like to do is to condense down an entire season's worth of hurricane activity for you. This is beginning back in July of 2005, running all the way out through December of 2005, illustrating the 27 storms that came up out of the Atlantic and hit the United States. And what we're looking at here is an amazing montage. We are putting cloud patterns on top of ocean surface temperatures. And we're doing this for 6 months, and we're compressing this down into about a 4-minute animation. And as each individual storm develops, you can watch it take its track up into the United States. Here we see one of the first storms of the season, Dennis. This is back in early July. You don't expect Category 4 storms to be striking the United States in July. Right on Dennis's heels, here comes Hurricane Emily moving up through the Gulf of Mexico, and you can watch these ocean temperatures just warm up drastically as the summer season wears on. It's important to realize or to understand that the source of energy for hurricanes is the ocean. The ocean is the source of fuel because of water vapor, and the water vapor evaporates from the ocean surface. Water vapor is the fuel that gets into the storms, that energizes them, that creates the warm core in the eye, that lowers the surface pressure. Now here we are. We're about to watch the formation of Hurricane Katrina, which is going to develop down here in the Caribbean and move up into the Gulf of Mexico. But before we get there, we do have a couple other interesting little storms. There's Katrina moving up into the Gulf Coast. And on the heels of Katrina, we do have Hurricane Rita that came along and followed much of the same trajectory. Here's an interesting storm, though, in the interim. This is Ophelia, and I'm not really sure what Ophelia had in mind because she dances around like a drunk sailor off the coast of the Outer Banks and has everyone scared to death for about 2 days about an impending landfall. Now here comes Rita, moving up over the very warm waters. These waters were approaching 30 degrees Celsius, which is about 87, 88 degrees Fahrenheit, like a jacuzzi in the Gulf of Mexico, if you will. And then finally, the big storm of the season, the strongest Atlantic hurricane ever to occur on record, Hurricane Wilma, will soon develop out here over the Caribbean waters and once again move up into the Gulf Coast of the United States. So we're going to explore why all these storms followed a very similar trajectory throughout this very, very long season. Okay, here comes Wilma. There she's tracking offshore. Luckily only clipped the very southern tip of Florida, spare the Gulf Coast. Now we got to get into the Greek alphabet because we've totally exhausted the alphanumeric alphabet, and we're getting into alpha, beta, gamma, all the way up to storm zeta. So we had quite a parade of storms in 2005. This is an amazing satellite sequence, and you can get this from the website. Now, what can I teach you folks as educators? How can we inspire our students? We have to use state-of-the-art visualizations such as this. We want to talk about the entire life cycle of tropical cyclones, from the birth of these storms through their maturity, all the way to their landfall and their demise. These African easterly waves are areas of low pressure. This is where moist tropical winds are flowing in, converging, and rising upward, forming giant thunderclouds. And there's a sequence of these waves. They're about every 3 to 5 days. New ones come off of Africa, 60 to 70 all told during the summer months. But only about 1 in 10 of these waves ever develops into a named tropical system. So we want to better understand, why are there so few tropical cyclones? Do any of you in the audience have any clues about some of the things that could limit the development of a cyclone in the tropics?
Water temperature.
Water temperature. Very good answer. There's a magic number for water temperature. I'm going to ask this question a little later on. So be thinking about what that magic number is and the other things you think interfere with the genesis of hurricanes.
Wind movement.
What's that? Can you speak a little bit?
Wind movement, direction.
Okay. So maybe something about the winds you're saying? If the winds are too strong, actually, that can interfere. That's called wind shear. Okay, so that's another destructive force. There's a new one that scientists have very recently learned about, and you have to study the Sahara Desert to understand what that is. Does that ring a bell in anyone's mind? Dust, plumes of dust blowing off the Saharan Desert actually interfere with the growth of these storms. I'll tell you a little bit more about that further on.
It has been said that a single flap of a butterfly's wings in Brazil can cause a tornado in Texas. And while that might be difficult to prove, it is true that the most powerful and destructive forces on Earth have to begin somewhere. Scientists from NASA and NOAA start studying hurricane genesis at a global scale using a fleet of Earth-observing satellites. With their eyes high above the troposphere, Terra and Aqua can watch as air masses traverse both continents and oceans. In some cases, such as this sequence of Isabel, their data can actually show us an air mass organizing into a hurricane. But wait, why do some clouds become cyclonic and not others? To answer this question, researchers travel across the Atlantic to Africa, where many of these systems, known by scientists as African easterly waves, have their origin. As many as 60 or 70 of these waves may stream off the African continent in a given year, yet typically only 1 out of 10 will actually develop into a named tropical cyclone. By flying specialized airplanes high above and right through the center of hurricanes and the cloud systems that form them, the scientists can collect measurements and try to deduce just what set of conditions are needed for a hurricane to take shape. As you might expect, there is no one single cause for a hurricane, but rather an intricate system involving wind, temperature, pressure, and a part of the atmosphere called the Saharan air layer. So while the flap of a butterfly's wings may be an ingredient, the entire recipe for a hurricane is one of incredible complexity that we are still only beginning to understand.
This constellation of satellites is called a sensor web, and it's about 27, 28 or so of these satellites that study all aspects of the Earth system, from vegetation to ocean temperature, cloud heights, rain intensity, aerosols, winds. All these elements factor into the genesis of hurricanes. But they only give us infrequent snapshots, kind of snapshots of opportunity as the satellite happens to pass over the right area where the storm is developing. Genesis is a continuous process, and we have to get out there with instruments on aircraft to get inside the circulations on the very small scales and follow these storms along for long periods of time. Now, one of my favorite aircraft that I've done a lot of flying on is the NASA DC-8. You can see it taking off here. It's a 4-engine, sophisticated turbojet aircraft that flies at about 40,000 feet. We can stay up inside a storm for 8 to 10 hours. There are many, many types of instruments on here that look at all aspects of water vapor, temperature, aerosols, which are particles in the air, precipitation intensity, wind speed, wind shear, ocean surface temperatures, you name it, we can measure it, we can sample it, okay? We even use these sophisticated instrument packages called dropsondes, which I'll illustrate the dropsonde here. It's a very portable device. I call it a $750 Pringles can because it's about the weight and shape of a Pringles can, but it's got, seriously, it has a GPS sensor inside of it so we can get the winds. It's got a parachute that comes out, and this thing actually descends down out the back of the plane through the atmosphere, and we get data coming back by radio in real time back to the scientists on the aircraft. Now, the next interesting aircraft that I've had the privilege of working with is the ER-2, which is a U-2 spy plane. It's been turned into a scientific observation platform. It flies at 70,000 feet, and that's so high that the pilot has to wear a spacesuit and pre-breathe pure oxygen like a diver does to avoid getting the bends. And this aircraft is also located, loaded with instruments. We use this to study a lot of the hurricanes developing off Africa and this last summer in 2006, and one of the most important pieces of the puzzle, as I mentioned, is to understand Saharan dust. Now, who would think that to study a hurricane, which is a moist cloud system with lots of thunderstorms and rain, that dust coming off Africa actually factors into the genesis of these storms. We found that dust is a hurricane suppressant. When the dusty air entrains or wraps inside the circulation, and by the way, as storms come off Africa, so do these dust clouds, and there's opportunities for these two type of systems to get intermingled with each other. When the dust comes in, it's not so much the dust that hurts the storm. We think it's the dry air associated with that dusty layer causes all those thunder clouds to evaporate. And when those clouds disappear, the storm has lost its energy source. Okay, so a key to a tropical cyclone surviving its journey across the ocean is to avoid dust clouds, develop really strong spin, and to stay away from wind shear, which can blow the tops of the clouds away from the bottoms of the clouds.
Forecasting a hurricane is no easy task. To do so, scientists must be detectives, gathering clues and evidence, attempting with the help of computer models to predict not only where a hurricane will move, but also how it will intensify as it travels along its path. Scientists at NOAA's National Hurricane Center take on this serious job, knowing they have both lives and millions of dollars of property on the line. In the past 2 decades, scientists have made great strides in their ability to predict a hurricane's path. This data visualization shows how the predicted track for Hurricane Ivan, seen here in green, was very close to the actual hurricane track, shown in yellow. Yet while these hurricane detectives can now tell, often to within a few kilometers, where a hurricane will make landfall, predicting how powerful it will be by this time still remains a bit of a mystery. Some tropical depressions intensify gradually over miles and miles. Other storms intensify explosively, catching coastal populations completely by surprise. Still other systems will never intensify into a hurricane at all. One of the forecaster's best tools in investigating hurricane intensification is a satellite called TRIM. This satellite takes CAT scans of hurricanes, revealing their inner workings so that forecasters can search for structures like hot towers and convective bursts, 2 signs that a storm may have the potential to organize into a hurricane. So while much about hurricane intensity remains shrouded in mystery, forecasters are starting to uncover integral clues that are leading to an ever greater understanding of these powerful atmospheric phenomena.
There's still a lot of unknown, and the forecaster has his or her nightmare scenario. And that nightmare scenario is the vulnerable Gulf Coast, where a hurricane can suddenly develop somewhere off of the Bay of Campeche or the Yucatan Peninsula, and within 24 hours be bearing down on a populated coastline of the United States. And what sometimes happens is, when people go to sleep at night, they hear that they're going to wake up the next morning to a Category 2 storm, which people can generally weather. But sometimes that storm will mushroom into a Category 4 overnight, and they wake up all of a sudden to an absolute monster approaching the shoreline. This scenario has actually happened. Hurricane Opal in 1995 went from a 2 to a 4 overnight while everyone was sleeping, and the forecasters completely missed the forecast. So we as scientists need to look for the physical clues. How can we use, for instance, satellite technology to help us identify when a storm is about to intensify? Well, one of NASA's great tools since 1997 has been this tropical rainfall measuring mission satellite, the first weather radar to fly in outer space. Looks down on the Earth. Now, a doctor, a general practitioner, will learn a lot about the body by taking an X-ray. You can look at the bony structure of the body, but that just tells you something about the framework. Analogously, in the 50s and 60s, scientists were only able to look at the tops of clouds. We couldn't see inside the clouds. But now, with satellites such as the TRMM satellite, uses microwave energy to penetrate inside those deep clouds. It's like taking a CAT scan of the entire storm. It's like looking at all those soft tissues and organs that we've never been able to see before. So this is a fabulous revelation to us as scientists. We're taking these 3D CAT scans, if you will, and this is a 3D CAT scan of Hurricane Katrina, looking at the different layers of rain intensity. Like peeling away the layers of an onion, we can look at the light rains on the outside and the heavy rains inside the core. We can also look at the vertical structure of these clouds. And you see these very, very giant clouds. You heard in the video, these are called chimney clouds. These are very deep thunderstorm clouds, and they lead to rapid intensification of a hurricane. Now, another example of a chimney cloud we will see is that for Hurricane Bonnie. Now, Bonnie was a powerful storm in 1998. This cloud goes up to about 12 miles into the atmosphere, which is one of the most giant clouds we've ever measured with this TRMM satellite. But here's what we found out about these storm clouds, something we didn't know 5 years ago. They're very, very frequent. They occur early on in the life cycle of many of these storms, okay? Water vapor, which is the fuel, rises up inside, it condenses and forms liquid water inside these giant chimneys. As the water vapor condenses, heat energy is released. Okay, that's what happens when you change the phase of water from vapor to liquid. That warms up the inside of these clouds, and these clouds then buoy up to giant heights. It's like turning on the hot air inside a hot air balloon, and the balloon just goes nuts, okay? Now, the air that goes up must come down, and as it comes down inside the eye of the storm, that air warms up inside the eye of the storm, and that is what creates the heart of the hurricane, which is called the warm core. It only makes sense that the taller these clouds and the longer lived these clouds are, the more energy they are releasing. And when this happens close to the center of circulation, they make the storm intensify. So the thunder clouds are the cylinders of the engine, but these chimney clouds are the turbocharged, fuel-injected cylinders in a souped-up sports car, if you will. When Isabel was developing across the Atlantic Ocean, we do know that several of these chimney clouds were erupting in rapid sequence when this storm was first developing. This is why we think Isabel went all the way to Category 5 and stayed at Category 5 for several days in a row. It's very rare for a storm to stay at Category 5 for this long, but Isabel did it, okay? Now, Isabel has been studied many, many ways. We've looked at the three-dimensional anatomy of the heat engine of this storm. There are many factors which push this storm to Category 5 intensity. First of which, as we've talked a lot about, is the warmth of the ocean temperature. That's a very critical factor. I'm getting ready to ask my question in a minute of the audience. Another factor is weak wind shear, and the weaker those winds, the more likely that storm is to remain vertically stacked, and that's very important if you're a hurricane, okay? But the water temperature is critical. The warmer the water, the more water vapor will evaporate. More water vapor will leave the surface of that water. The vapor is the fuel of the storm. A very tiny rise in sea surface temperature can lead to an exponential increase in the amount of fuel available for that storm, and the faster the hurricane engine will rev. The Atlantic sea surface temperature is the critical element for giant storms such as Isabel and also for the big storms of 2005. Water has the highest heat capacity of any natural substance. That means it takes a lot of solar energy to raise the water temperature. Now, in the sequence I'd like to show, we can see the warm ocean temperatures increasing throughout the summer and fall months from the vantage point of satellite. Just watch these waters warm up. July, August, September. It takes many months for these waters to warm because of the heat capacity. The Atlantic has to incubate under the hot tropical sun, so the waters are not ready for activity until the early fall months. Now, here's the question. What is the magic sea surface temperature needed to get a hurricane anywhere in the world? You can say it as Celsius or Fahrenheit. How about the lady wearing the red vest? Can you give me an answer? Yes, you. I can actually pick on students. This is temperature.
I would guess 75. 75 degrees Fahrenheit.
Okay, that's pretty much it. 26 degrees Celsius, 75 degrees Fahrenheit. You win the prize, okay? Very, very good job. All right, we'll give ourselves a hand, okay? Temperature of the water is only skin deep, because we have to look at the deeper layer of water as well. It's not just the skin temperature, but it's how far down in the ocean column that warm water extends. So we call the depth of warm water the thermocline. And you can think of the thermocline as a giant reservoir of heat in the upper layers of the ocean. And we want this thermocline to be really, really deep, because what happens is, as a hurricane moves over, the vortex winds stir up the surface of the water, and they mix up cold water from the deeps. And when the cold water comes up to the surface, there's less evaporation, and you see the engine starts to run down, okay? So the deeper that layer, the more resistant it's going to be to the mixing up of the cold water. This was the case all throughout the summer and fall of 2005, throughout the Gulf of Mexico. That thermocline was incredibly deep throughout the Caribbean, the Gulf of Mexico.
Much like the gas engine in your car, a hurricane is a heat engine, taking the energy trapped in warm ocean waters and converting it to wind and rain. Let's open up the hood and take a closer look at how this heat engine works. The first thing our hurricane heat engines need is fuel. In this analogy, the entire ocean can be considered to be our gas tank, and the fuel is the warm, humid air resting atop the tropical oceans. We can judge by sea surface temperatures just how gassed up we are. The hotter and more widespread the warm surface waters, the more potential we have for a powerful and enduring hurricane. As a tropical cyclone moves across the open ocean, it uses up its fuel, leaving behind cold water trails, as you can see in this visualization of Fabian and Isabel. But now let's look inside the engine. A hurricane works with the eyewall clouds acting as cylinders to which our water vapor fuel rises and cools. As the cylinders heat up, they rise higher and higher, spreading out as they go. Rather than releasing energy through combustion like a car engine, hurricanes liberate latent heat energy through enormous amounts of condensation and freezing. When the now rapidly cooled air spills out of the eyewall cylinder, it sinks back down towards the sea. The rising and falling air patterns, combined with the rotation of the Earth, create our engine's drive shaft, maintaining its form and propelling it along its path as long as fuel remains. The exhaust fumes are storm clouds, filled with the only byproduct of condensation, which of course is a whole lot of rain.
There is an analogy that I like to use between the natural heat engine in the atmosphere called the hurricane and a car engine. Now, the one shortcoming here is that perhaps students these days really don't know what goes on under the hood of a car. And that's a little frightening, especially now the days with hybrids are coming out with electric motors. This theory no longer applies, and I'm out of a job right now, okay? But let's take a little quiz. Let's play the hurricane game, okay? I'm going to put up a cartoon, if you will. This is something I do with my students in my class. The top part shows the major components of the automotive engine, okay? And in the bottom here are the fill in the blanks. So let's start off really quick. What is the fuel tank of the engine? Okay, good. So you got that right. Let's see if we can go for 100% here. What's the fuel for the hurricane? Water vapor. Excellent. Okay. Now, how about the fuel pump? Now, the fuel pump is the device that draws in the fuel from the tank into the engine. You got to think hard about this one. What could the fuel pump be in the atmosphere?
Wind?
Wind. Yes, it's wind. It's the winds that are spiraling in and converging, drawing in all that moisture where it rises up into the cylinders. Now, in the hurricane, what part of the storm is analogous to the cylinders? The eye wall clouds, the thunder clouds. Yes, very good. Now, in the engine, we have combustion, where fuel is converted into motion and heat is released. What do you think is the analogous process of combustion in the hurricane? Condensation. You guys are doing wonderful. This is fabulous, okay? The flywheel. Now, the flywheel is the heavy wheel that's connected to the crankshaft. The pistons are rotating energy, and this is really the rotary motion of the engine. In the hurricane, what is the flywheel? It's the vortex. It's the rotating winds of the storm, right? And then finally, the exhaust. The exhaust is the noxious stuff that comes out and pollutes our air in a car engine. But in a hurricane, what could the exhaust be?
Rain.
The rain and the clouds. Oh my goodness, this class gets 100. I say fabulous. Very, very, very good job. Okay? Wonderful. No one in my class has ever gotten this right, so you're the first. This just brings everything together I just explained to you, going back to the cartoon, which is really nice. You see all these little sparklies zipping around this cloud. That's our attempt to illustrate latent heat. This is our attempt to illustrate that when water vapor condenses into liquid, all this heat energy gets released, okay? So basically you have condensation, which warms up the air inside these giant chimney clouds. The air rises like it's going up in a hot air balloon, and then as the air hits the top of the tropopause, it must spread out in all directions. And as it does so, some of the air comes back down in the center, right back down the eye of the storm. And when that air comes down, something important happens to it. It compresses and it warms. Much like you take a bicycle pump and you pump it up really hard and you feel the metal cylinder, it gets hot. That's from compressing air. And it's that warm air that builds inside the eye that gives the hurricane its real energy, because this warm air is being trapped by the rotating winds of the vortex. It can't escape. And when the column of air gets warmed up, the density of this molecules are exerting less pressure on the surface, and that's why a column of warm air means that the pressure drops right above the ocean surface. The air rushes in to fill the low pressure void, and lo and behold, a hurricane is born. You see, these storms become kind of self-sustaining after a while. The inflow creates more rising motion, which creates sinking in the eye, which warms up the interior, which brings in more air. It's self-sustaining. this storm released 750 million 1 megawatt power stations equivalent in the 14 days of its existence. 750 million 1 megawatt power stations came out of this storm. That's enough energy, folks, to burn light bulbs covering every square inch of the entire state of West Virginia from one hurricane. Now that's a lot of light. That's a lot of power out of one of these storms. And you ask yourselves, how can we tame this? I have to laugh, because I don't know how we as humans can tame these storms right now. It's ironic that the thermodynamic efficiency of this hurricane heat engine is really, really small. In other words, only a very small percentage of all that heat that gets released actually goes into the kinetic energy of the winds that spin around that vortex. Here's Hurricane Erin, another three-dimensional view of the structure of this storm. We can look at the anatomy of the storm using satellites and aircraft data. You can see the outline of the cloud, and inside the green area indicates the heavy rain that's falling out. This is the condensation, the byproduct, the warm core you can see here in the upper troposphere. This was measured by these dropsondes put down by the ER-2 aircraft. We're actually able to examine all the parts of this hurricane engine in 3 dimensions. We could never do this 5 years ago.
Some hurricanes make quite epic journeys, slowly moving from Africa all the way across the Atlantic, maturing and intensifying over miles and miles of open ocean. And as a now mighty hurricane nears the U.S., we ask what it is that steers a hurricane towards land, and moreover, what are the forces that weaken and eventually destroy them? A key factor in answering these questions involves an area of high pressure over the Bermuda Islands. This area, known as the Bermuda High, plays a major role in determining the path of a hurricane once it reaches the western Atlantic Ocean. Some years, this area is small, and hurricanes are steered north over the ocean. When this is the case, a hurricane generally weakens due to cooling sea surface temperatures and high wind shear. Such a hurricane may dissipate without ever actually making landfall. On other years, though, the Bermuda High is large and storm systems are pushed towards the Gulf of Mexico. The hurricane picks up additional fuel from warm Caribbean waters before turning north and heading for land. At landfall, however, a hurricane quickly finds itself out of gas. Without the conditions to sustain it, the hurricane heat engine breaks down. Yet with its demise imminent, a hurricane rarely goes quietly. Still storing enormous amounts of energy, the hurricane releases it in the form of rain. The staggering amount of water dumped by a single hurricane has been calculated to be enough to fill Lake Erie. As a consequence of such a large amount of rain, freshwater flooding is the #1 cause of hurricane deaths. Nevertheless, within days after making landfall, the hurricane finally meets its finish. If they are prepared, people and their belongings weather the storm and turn their eyes back to the ocean, watching for the next developing system already traveling on its long trip across the Atlantic.
Hurricane Isabel, as I say, started off as Cat 5, but she went down very suddenly to a Category 2 just 24 hours before landfall. And this was not very well predicted. As a matter of fact, when Hurricane Isabel spun down, the diameter of the storm expanded greatly. So it was kind of a collapse of the vortex. And although this was good that the wind speed went down, the strong winds were projected over a much broader area. And that's why so many in the mid-Atlantic lost power from this enormous storm as it went up through Virginia and Maryland. There are many forces that conspire to weaken the storm. As the storm moves towards higher latitudes, of course, the storm encounters colder water temperatures, less evaporation, less fuel. I think you get that picture by now. Certainly, as the storm approaches the United States and the jet stream coming out of the western part, there's more wind shear that the storm encounters. So the wind speeds pick up in intensity, and so the storm gets ripped apart. Also, the other thing you have to consider is that when the storm sits over a landmass such as the United States, there's a lot of dry air here, and the dry air can get pulled off the continent into the United States. What's interesting to note is this Bermuda high in 2004 had shifted to the south and west across the Caribbean and actually steered a lot of those storms that otherwise would have recurred safely out over the ocean into Florida. That's why so many storms hit in 2004. And in 2005, this high pressure area still to the far south and west steered a lot of the storms even further west up into the Gulf of Mexico. So there's a reason for you right there why 2004, 2005 were so bad in terms of number of landfalling major hurricanes. We heard a lot of talk in our sequences about how storms leave behind this cold trail of water. And in the case of Isabel, you can see Isabel moving from kind of southeast northwest here, went right across the cold trail of Fabian, but it really didn't put too much of a dent in Isabel because she crossed it so quickly and at such an acute angle. Had that storm tracked more along the trail of Fabian, certainly we would have seen the impact much more serious on the storm's intensity. Dying gasp of a hurricane, when it makes landfall, it still is importing a tremendous amount of tropical moisture with it. Landfall impacts include storm surge, damaging winds, and freshwater flooding. Now, of those three factors during hurricane landfall, which do you think claim the most lives in the Western Hemisphere? Storm surge, flash flooding, or hurricane winds? Well, not all at once. Okay. We have a consensus here, maybe. What's the #1 killer in the Western Hemisphere? Flash flooding. You got it. Right on. Okay. It is flash flooding. This is flash flooding due to heavy rains. This is river flooding due to rapid rise in river stage. Okay. And in the mid-Atlantic, we have certainly set the stage for some biblical floods in the past from these tropical storms. Hurricane Camille dropped 3 feet of rain in the space of 8 hours on a little tiny county in central Virginia. Okay? There are some absolutely astronomical rains that have come out of these clouds. What's interesting to note is that the strongest category storms are not necessarily correlated with the heaviest rainfalls. We often find that the weaker storms, the Category 1 storms, even tropical storms or tropical depressions, actually cause more flooding than do these major hurricanes. Okay, so that's just one of the difficult aspects of forecasting these storms. It's difficult to understand what their rain potential is going to be in the days before landfall. There are many influences, such as mountain chains, such as frontal systems, such as jet streams, that begin interacting with the remnants of these storms, and all this tropical moisture has got to go one way, and that is down towards the ground. In this particular sequence, we could look at the track of rain being laid down by Isabel as she came up out of the Atlantic. The reds here indicate rainfall in excess of 1 feet. But as the storm made landfall, the rains very, very quickly died off. So here's a case of a storm that didn't produce a lot of rain when we thought that it might produce a lot of rain. And as you heard before, enough rain came out of Isabel to fill the entire Lake Erie Basin. That's a calculation that I did. I computed that it was about 88 billion tons, between 88 billion tons and about 144 billion tons, depending on some of the assumptions you make about these calculations. But that's an awful way to dampen your parade, is that much rain. The main effect of these storms is that they have global impact. They move excess energy out of the hot tropical latitudes towards the cold polar latitudes. They help maintain the heat balance of the planet, if you will. And that's the fundamental thing that storms do on this Earth. They're also, while they do produce bad flash flooding, they can at times produce beneficial rainfall for many countries. You know, parts of the southeast United States depend on the regular occurrence of landfalling hurricanes to recharge aquifers and to get these places out of their summer-long droughts. They promote the health of forest ecosystems because these damaging winds come through and clear out a lot of the old, weak, diseased trees in tropical forests and allow the forests to rejuvenate. And they certainly are potent agents of beach erosion, deposition of sand. They also cause barrier islands to shift over time. And we know that human beings love building towns on barrier islands. Galveston, Texas is a great example of a barrier island built that was destroyed in 1900. And in the Atlantic Ocean, we think that these hurricanes drive this giant overturning of warm water flowing north and cold water flowing south called the thermohaline circulation. It's a giant conveyor belt of water. And we think this thermohaline circulation actually regulates the Earth's climate on short time scales, and hurricanes may actually help to drive this.
"27 storms, Arlene to Zeta." Let's examine what made conditions so favorable for Atlantic storm formation in 2005. We begin with the ocean. These are sea surface temperatures for the 2005 hurricane season, changing through time as the calendar advances. Warm water powers hurricanes. Orange and yellow areas show zones with water warmer than 82 degrees, the threshold favorable for hurricane development. Let's start the season again, this time adding clouds back into the picture. Atlantic Basin hurricanes typically form between June and November. Hurricanes often start as atmospheric disturbances off the coast of West Africa. Once out into the warm summer waters of the mid-Atlantic, some ripples begin to rotate and, feeding off of warm water, strengthen into hurricanes. Hurricanes require warm water to heat air above the ocean, causing a drop in air pressure. Lower air pressure sucks more water vapor into the storm, causing storms to strengthen. As hurricanes pass over warm water, they leave trails of relatively cooler water, so-called cold water trails. Numbers displayed over storm tracks indicate hurricane category changes. Strong shearing winds in the troposphere can disrupt this process, weakening young storms. But measurements indicate that there was very little shearing wind activity in 2005 to impede storm formation. Hurricanes are rare phenomena. Only about 80 or 90 appear worldwide every year. Storms stalked the Atlantic Ocean and eastern seaboard from June until early winter in 2005, and the record books are groaning under the strain of such a busy year. Consider this list of superlatives. An average year produces roughly 10 storms. 27 named storms formed in 2005. An average year produces 6 hurricanes. 15 formed in 2005. An average year produces 2 major hurricanes. 7 formed in 2005. On average, 1 Category 5 hurricane forms every 3 years. In 2005, there were 3, Katrina, Rita, and Wilma. Wilma was the most intense Atlantic hurricane ever recorded, Katrina 4th, Rita 6th. But Katrina was the most destructive hurricane ever to hit the United States. The total losses from storms in 2005 include more than 1,200 lives and potentially more than $100 billion. This visualization shows some of the actual data that NASA and NOAA satellites measured this season, data used to predict the paths and intensities of hurricanes. Satellite data play a vital role in helping us understand the land, ocean, and atmosphere systems that have such dramatic effects on our lives.